So, number one, hydroiodic acid. Listen to my words. You're checking your paper. You're asking questions if you have them. Yes? The first, like 4 or 5, I'm going to do rather slowly and deliberately, and then I'm just going to crank out the answers for the remainder. Got it? Okay. Hydroiodic acid. You see this name, you have to write the formula. So, it's an acid, which tells you that it has hydrogen in it, regardless of whether hydro is in the name. The word acid tells you it has hydrogen in it. Yes? So we're going to start with hydrogen with a 1+ charge. Iodic tells you that it's hydrogen going together with iodine. Iodine has -1 charge. Crisscross drop reduce, you get capital H, capital I. Okay? All right, number 2. H3PO4. You're starting with a formula. You have to write the name. You see that the formula starts with hydrogen, so after today you should think acid. That is an acid. Why? Because it starts with hydrogen and it ain't water. Correct? So it's an acid. I have hydrogen going together with phosphate. Phosphate. So I don't use hydro at the front. I change the ending of the anion to ic. It was 8. Now it's ic. And then I tack the word acid on the end. So the answer for number 2 is phosphoric acid. Phosphoric acid. Now, number 3, we're writing the name. It starts with hydrogen, so right away I should know that it's an acid. Okay? It's hydrogen going together with an element, correct? It's hydrogen going together with an ide, phosphide. So because it's not going together with the polyatomic, I need the prefix hydro, then I need the phospha, and I need the ic, and I need the acid. So hydrophosphoric acid. Number 3, hydrophosphoric acid. Do you see on these two, number 2 and number 3, what I was saying a couple minutes ago? Sort of a complicated formula, H3PO4, short name, phosphoric. Sort of a simple formula, H3P for number 3, sort of a long name, hydrophosphoric acid. Yes? Okay, so number 4, carbonic acid. I have an acid, it's hydrogen and something. There's no hydro in the name, so it's going to be hydrogen going together with a polyatomic. What polyatomic starts with carb? Carbonate. What is the charge on a carb? What's the formula for carbonate? CO3. What's the charge? -2. So my formula is H2CO3. Beautiful. Troubles? All right. Number 5, nitric acid. Again, we have an acid. We know that because it says acid. Oh, jiggle the mouse, please. Thank you very much. Okay, so we have an acid, so we know that it's hydrogen, but there's no hydro at the front. So it is hydrogen going together with what? Nitrate. Nitrate, which is, what's the formula? NO3, what's charged? -1. So HNO3. HNO3 for nitric acid. Troubles? Okay, now quick, fast answers. If you have trouble, you need to let me know. So number 6, H3N is hydronitric acid. That is the correct name. That's the answer for number 6. Hydronitric acid. Number 7, hydrobromic acid. Capital H, capital B, little r. HBr. Number 8 is hydroiodic. Number 8 should have taken you back to number 1. Number 1's answer is number 8. Number 8's answer is number 1. You follow? All right, number 9, acetic acid. Now, this one's interesting. I got hydrogen with a 1 charge. I got acetate, which is C2H3O2 1- charge. crisscross drop reduce, you get H, C2, H3, O2. Do not put the hydrogens together somehow so that you have C8, C2, H4, O2. Do you follow what I'm saying? Why can we not do that?
That changes the number of...
You're correct, it's not right. But if I did that, if I had 2, 4, 2, I can't change the polyatomic. I can't change the polyatomic. And if I tried that and I did that, I would have to take the 2 and the 4 and the 2 and do what with that ratio? Reduce it. Well, now you're not even close to what we're talking about. Okay? So yes, it's strange that you've got H, C2, H3, O2. You've got those H's separated in there. It doesn't matter. Okay? That's the formula for acetic acid. Now, hydrofluoric acid. It has hydro in the name, which means that it's going together with a single element, in this case fluorine. Capital H, capital F. Formula. Fluorine has 1 charge. Crisscross drop reduce 1, 1. Yes? Okay. Groovy. Y'all can tuck that away. We may or may not finish metallic bonding today. We only have 10 minutes, well, 12 minutes or so left, but there's only 2 slides. I don't think so. I don't think so. I don't think we're taking a quiz tomorrow. Yeah. Okay. By the way, I've scheduled a remind to go to you guys, I don't know, around supper time tonight about bringing the hotel and travel size dooflatches. Do I need to send that to you tomorrow night and Wednesday night also? Like every night?
You should also send one at 9 o'clock tonight, because that's when I get off work.
Just do it every day.
And I'll bring you some tomorrow.
Every hour of every day until Thursday? Or I don't know what you guys are like. I want one at 9.
Twice.
I want one at 6:30 a.m.
Once every day.
Well, actually.
Do you work until 9 tonight?
And then 12 tomorrow, and then 12 the next day.
Okay.
But you work until 9 tonight?
Yes.
I'll schedule one for 9 tonight.
Wish Liz liked me as much as she does.
I know. True. Sorry, dude.
What are you talking about?
Liz
I
is the
get
person
like
that's...
1 day a week, and then this one right here is about to go over his limit every week.
True.
Oh, is this your manager at the...
This is Liz. She's the front end manager, or not front end. She's the front cashier, and she schedules everybody. And
She's a something.
Okay. All right. Is she acidic?
Yeah.
Because I think that's like a step worse than salty, right? Like you can be salt,
toxic.
but then you can be acidic, which is like worser.
She's
I told her,
She's
like, hey,
cancerous.
call me, I need hours. And she's like, okay,
They should
we'll
only
do
get
it.
like 1 4 hours.
Deadly.
Yeah, one payday I got 4 hours.
That's okay.
No, it's
That's
not.
like-
That's like $28.
I've gotten 3.5 hours.
Hey, they're 5.
Stanford's winning.
Stanford.
Wait,
I
you
got-
work at the food city?
I got called in
Sure,
twice
so
this weekend, so
Oh.
I have.
I was like, I haven't
I'm
seen
on my
Stanford
limit
there,
right now.
because she only works 3.5 hours. Okay. All right, here we go. So metallic bonding. Okay? When we talk about metallic bonding, we're really talking about the chemistry that the metals do together. Do you follow what I'm saying? If I have a metal, which is a cation going together with an anion, that's a left plus right. That is ionic. That is not metallic bonding. Metallic bonding is 2 metals going together. And they don't go together because they have opposite charges. Okay? The metals that do this most often are the transition metals, going together with other transition metals, or the group 1 or group 2 metals going together with transition metals. Okay? Now, the valence arrangement for many metal atoms can be described as and is described as a sea of electrons? Now, what do you guys know about the sea, the SEA? Describe the motion of the ocean for me. There's waves, right? So it's a constant movement,
Yes.
and there is an ebb and a flow, correct? An ebb and a flow. So there's back, forth, back, forth. If you guys have ever been on a raft or on your boogie board or whatever, out past where the waves are breaking, you're not still. You're not out there treading water like you are in a swimming pool. There's up down. Do you understand what I'm saying? You're not moving forward or backward, but there's up down. Okay? And that's the ebb and flow that we're talking about. With transition metals, those electrons drift from one energy level to another. This is why, and I think it's actually up here. Yes. This is why transition metals have varied numbers of valence electrons. We can look at the transition metals, we know they lose electrons and become cations with positive charge. But if I look at iron right now, it's got one valence electron, but iron can have two, can have three, can have four. Well, why is that? Iron doesn't change the number of electrons it has. Those electrons don't behave in a, quote, ordinary way. They do this drifting thing. Oh, right now I'm gonna circle the nucleus in the fourth energy level. I don't want to hang out there anymore. Now I'm going to circle the nucleus in the third energy level. And now I'm going to go back to the fourth. And now I'm going to go back to the third. This is why the drifting, the ebb and flow, is why transition metals are weird. You look at somebody in group 1, one valence electron becomes an ion, 1 plus charge. Cut and dry, black and white, straightforward all the time. You look at somebody in group 16, 6 valence electrons, they tend to get 2, become an ion with 2 minus charge. Straightforward, cut and dry all the time. And then there's the transition metals. They just do what they want. Okay? Oops. Anybody not done? This slide, by the way, is the last slide for metallic bonding. Because we started and finished it in 10 minutes. Truly. Now, what is metallic bonding? Metallic bonding is the attraction of two metals to each other, or the bonding of two metals to each other. And why does metallic bonding occur? It happens because there is an attraction of these free-floating ions with the positive ions that tend to form in metals. Now, here's the thing that you need to remember about metallic bonding. It's not very strong. We just spent an entire week learning about ionic bonding and ionic compounds. Like, we put some time into that. Metallic bonding is very simple and it's very straightforward. It's just two or more metals going together. Okay? The only reason they go together is because you've got these electrons that drift, and then you've got metals, how they tend to form positive ions and the drifting electrons, and so there's a very loose attraction between them. And I don't use that term loose lightly. It is a very weak attraction between them. This is not ionic bonding. That's a complete positive, complete negative going together. And we're not doing that. Okay? So, metallic bonding is, in general, the tendency of metal atoms to be with other atoms of the same element. What does that mean? That means copper atoms hanging out with a whole bunch of other copper atoms. or copper atoms hanging out with silver atoms. Interesting information. At least I think it's interesting. Atoms that make up metals. If you have a substance, like suppose you have a sample of aluminum metal, just solid aluminum metal. Those atoms, the multiple atoms that make up that sample that you're holding in your hand, for example, those atoms line up in a very geometric fashion. What that means is the atoms would be, if this room was a little bit straighter, the atoms would be lined up the way that the desks are in here. So roughly equidistant apart, front, back, side to side. That's what we mean by geometric. As opposed to two atoms that are super close together, and then some atoms that are further apart, and sort of like crazy. Okay? That's what I mean by very geometric fashion. So what that means is that metals, groups of atoms of a metal, okay, so a sample of, as I said a minute ago, aluminum, for example, they are crystalline. When you see the word crystal, what kind of things come to mind? Like if you came upon a crystal, how would you describe that maybe? Sharp, okay. What? Sometimes they're shiny, like because they reflect light a lot, right? Okay, what else? You might think of a prism, okay? Do any of you guys think of them as being transparent? Like, can you see through them usually? So if you had a crystal and you laid it down on something blue, it would appear blue, okay? And that's correct. It's okay to think that way, and that's what we think of as crystals. But metals are actually crystals. You can't see through them. But what makes a crystal is the way that the atoms or molecules line up. Okay? Now, an alloy. This is a term that you need to know. An alloy is a mixture of two or more metals. For example, sterling silver is an alloy that is made specifically of 93% elemental silver and 7% copper. Most people think of sterling silver because it's expensive as being more pure silver than, I don't know, something else. Okay? But sterling silver is silver that is alloyed with copper for a very specific reason. It gives it some resistance to tarnishing, and it gives it some hardness. Elemental pure silver is very, very soft, such that we could not make jewelry out of it and have it last for any length of time. Another example. Bronze. If the bell rings, you're not going anywhere. We're finishing these notes. Bronze is a mixture of copper and tin. What the ratio is, I'm not sure, but it's copper and tin. Steel, which we've actually talked about a couple times. Steel is a mixture of iron and carbon and some other metals. What do we know about galvanized steel?
It's got zinc in it.
It's got zinc in it. So galvanized steel is iron and carbon and zinc, specifically. No quiz tomorrow. We're going to start covalent bonding tomorrow. We will probably definitely take a quiz on Wednesday.